Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Ronald Aylmer Fisher's 1937 monograph, The Design of Experiments, represents a watershed moment in the application of statistical thinking to scientific inquiry. It is an intellectual achievement that transcends a mere compilation of techniques. Instead, it established a new paradigm for how experiments should be conceived, conducted, and analyzed, particularly within the agricultural sciences, from which Fisher himself drew substantial inspiration. This essay will delve into the historical context, the core ideas espoused within the book, its immediate and long-term impact, and the criticisms and revisions it has undergone, highlighting the profound influence it continues to exert on scientific methodology. The intellectual landscape preceding Fisher's work was often characterized by ad hoc experimental designs and subjective interpretations of data. Agricultural research, in particular, suffered from a lack of rigor, with conclusions frequently drawn from uncontrolled observations. The prevailing approach often involved varying multiple factors simultaneously, making it impossible to disentangle their individual effects. Moreover, the importance of randomization and replication was poorly understood, leading to biased results and unreliable inferences. Carl Pearson's statistical approaches, while pioneering, focused primarily on observational data and correlation analysis, offering little guidance for designing effective experiments. William C. Lee Gossett, through his work on the t-distribution under the pseudonym Student, had addressed some of the limitations of small sample sizes, yet a comprehensive framework for experimental design remained elusive. Fisher's genius lay in synthesizing these disparate ideas into a coherent and practical system. The design of experiments articulated several fundamental principles that revolutionized experimental practice. Foremost among these was the concept of randomization, which Fisher advocated as a means of ensuring the validity of statistical tests. Randomization, he argued, protects against unknown sources of bias by distributing them evenly across experimental units. This simple, yet powerful, idea allowed researchers to estimate the effects of treatments without having to explicitly control for every conceivable confounding variable. His text explained how to use random number tables or equivalent mechanisms to assign treatments to experimental units, thereby creating a foundation for valid inference. Replication, another cornerstone of Fisher's approach, addressed the problem of natural variability. By repeating each treatment multiple times, researchers could obtain more precise estimates of treatment effects and assess the magnitude of experimental error. Fisher emphasized the importance of adequate replication, cautioning against drawing conclusions from experiments with insufficient statistical power. He introduced the analysis of variance, often abbreviated as ANOVA, technique as a powerful tool for partitioning the total variation in the data into components attributable to different sources, for example, treatments, blocks, and error. The analysis of variance framework allowed researchers who formally test hypotheses about treatment effects and to quantify the uncertainty associated with their estimates. This discussion of the F distribution, derived from the ratio of variances, provided the statistical basis for comparing treatment means and assessing statistical significance. The concept of blocking also received extensive treatment. Fisher recognized that experimental units are often heterogeneous, and that this heterogeneity can obscure treatment effects. Blocking involves grouping experimental units into relatively homogeneous blocks and then randomly assigning treatments within each block. This strategy reduces the impact of extraneous variation and increases the precision of the experiment. The design of experiments detailed various blocking schemes, including randomized complete block designs and Latin square designs, each tailored to specific experimental settings. The Latin square design, for instance, which arranges treatments such that each treatment appears exactly once in each row and each column, is useful when two sources of extraneous variation are present. Factorial designs, perhaps Fisher's most innovative contribution, enable researchers to investigate the effects of multiple factors simultaneously, rather than conducting separate experiments for each factor. Factorial designs allow for the estimation of main effects, that is, the average effect of a factor across all levels of other factors, as well as interaction effects, which occur when the effect of one factor depends on the level of another factor. Fisher argued that factorial designs are more efficient and informative than one factor at a time experiments, as they allow for the detection of interactions that would otherwise be missed. He described how to construct and analyze factorial designs, including 2 to the power of n designs, where n represents the number of factors, which are particularly useful for screening a large number of factors in early-stage experiments. The immediate impact of the design of experiments was profound, particularly within agricultural research. The Rothamsted Experimental Station, where Fisher worked for many years, became a hub for the dissemination of his ideas. Researchers from around the world flocked to Rothamsted to learn about the principles of experimental design and to apply them to their own work. The book quickly became a standard reference for agricultural scientists, and its influence spread to other fields, including biology, medicine, and engineering. Specific earlier applications included optimizing fertilizer treatments for different crops, evaluating the effectiveness of new pesticides, and improving breeding programs for livestock. The statistical methodology described within became commonplace. The long-term impact of the design of experiments is difficult to overstate. Fisher's ideas have profoundly shaped the way scientific research is conducted across a wide range of disciplines. His emphasis on randomization, replication, and factorial designs has become integral to the scientific method. The analysis of variance has become one of the most widely used statistical techniques in the world. The concepts presented continue to be taught in introductory statistics courses. Beyond its direct impact on experimental practice, the design of experiments has also stimulated further theoretical developments in statistics. The field of optimal design, for example, seeks to find the experimental design that maximizes the amount of information obtained for a given cost. This area builds upon Fisher's ideas about efficiency and information, and it has led to the development of sophisticated algorithms for constructing optimal designs in complex settings. The theory of response surface methodology, which is used to model the relationship between a response variable and several predictor variables, also owes much to Fisher's work on factorial designs. Despite its immense influence, the design of experiments has also been subjected to criticisms and revisions. Some statisticians have argued that Fisher's emphasis on significance testing can lead to over-reliance on p-values and a neglect of effect sizes. The p-value, representing the probability of observing data as extreme as, or more extreme than, that observed, assuming the null hypothesis is true, is often misinterpreted as the probability that the null hypothesis is false. Critics argue that effect sizes, which quantify the magnitude of the treatment effect, are more informative than p-values and should be given greater weight in the interpretation of experimental results. Confidence intervals, which provide a range of plausible values for the treatment effect, are also seen as a valuable complement to significance tests. While Fisher himself acknowledged the importance of effect sizes, his emphasis on significance testing has been interpreted by some as an invitation to focus excessively on statistical significance at the expense of practical significance. Other criticisms have focused on the assumptions underlying the analysis of variance. The standard analysis of variance assumes that the data are normally distributed and that the variances are equal across treatment groups. These assumptions are often violated in practice, and violations can lead to inaccurate inferences. While robust methods have been developed to address these issues, their application requires careful consideration of the specific experimental context. The assumptions required for implementing the analysis of variance must be validated to verify that its implementation is accurate. Furthermore, some have argued that Fisher's focus on classical experimental designs can be limiting in certain situations. In observational studies, for example, where treatments are not randomly assigned, classical experimental designs are of limited use. Causal inference methods, such as propensity score matching and instrumental variables, have been developed to address the challenges of drawing causal inferences from observational data. While these methods do address some of the shortcomings, Fisher's designs continue to offer useful insights. The reception of the design of experiments was generally positive, although some statisticians initially found its ideas challenging. Fisher's emphasis on randomization and factorial designs represented a departure from traditional approaches, and some researchers were reluctant to adopt his methods. However, the clear and persuasive writing style, combined with the practical examples provided in the book, helped to overcome this resistance. The examples, based largely on real-world experimentation, demonstrated the utility of the techniques. The book also benefited from Fisher's strong personality and his willingness to engage in debates with his critics. Fisher was a forceful advocate for his ideas, and he was unafraid to challenge established dogma. His conviction and his intellectual rigor helped to solidify the position of the design of experiments as a seminal work in the field of statistics. The work also represented a departure from existing norms. The design of experiments was directly influenced by Fisher's own experiences as a statistician at the Rothamsted Experimental Station. His work on agricultural data exposed him to the limitations of existing experimental methods and motivated him to develop a more rigorous and efficient approach. He also drew inspiration from the work of earlier statisticians, such as Carl Pearson and William Seeley Gosset, refining and extending their ideas to create a comprehensive framework for experimental design. His personal experiences contributed materially to the influence of the design of experiments on subsequent works is extensive. Countless textbooks and research articles have built upon Fisher's ideas, extending them to new areas and refining his methods. The book has inspired generations of statisticians and scientists to think more carefully about the design and analysis of experiments. Specific examples include the development of response surface methodology by George E. P. Box and his colleagues, which builds upon Fisher's work on factorial designs, and the development of optimal design theory by Jack Kiefer and others, which seeks to find the experimental design that maximizes the amount of information obtained for a given cost. Subsequent works built on the foundation laid for them. In conclusion, the design of experiments is a monument to statistical thinking and a testament to the power of rigorous scientific methodology. While criticisms and revisions have refined some of its details, its core principles of randomization, replication, blocking, and factorial designs remain as relevant today as they were in 1937. Fisher's work has not only transformed the practice of scientific research but has also inspired further theoretical developments in statistics, solidifying its place as a landmark achievement in the history of science. Its impact extends far beyond the agricultural context in which it was conceived, influencing diverse fields and shaping the way we approach empirical inquiry. The text remains a critical contribution to the scientific discourse.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.